Very good evening to everyone, and welcome to the NPTEL second live interactive session for the course Mechanical Behavior of Materials. The course instructor for this course are Dr. Shashank Shekhar and Dr. Sudhanshu Shekhar Singh from the Department of Material Science and Engineering, IIT Kanpur. I am an additional TA Shubham Jaiswal. I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. So in this live interactive session, we will be going to solve some samples problem which are related to your week content and also somewhat similar to your weekly assignment, which will in turn help you to solve your weekly assignment. So, am I audible? Okay. So in this live interactive session, so for today we will solve the assignment 1 first. Then we will quickly recapitulate about the what are the things we have learned in week 2, and we will solve some concept related questions. So coming to the assignment 1, the first question is like that: among the following, which material has the highest modulus of elasticity? So can anyone answer? So, to answer this question, we need to draw the potential energy curve and versus. Am I audible, Mr. Yogesh and Mr. Karthik?
Yes, you're audible.
Yeah. So, so to answer this question, we will need to draw the potential energy curve. So can anybody tell among the following which material has the highest modulus of elasticity?
Steel, sir.
Steel. And why is it so?
Because of the stronger bond.
Okay. So here we have concrete. It is type of a composite. And second, we have steel. It has a metallic bonding. Okay. Also, the concrete has covalent plus hydrogen bonding. And aluminum has metallic bonding. And the rubber has, which type of bonding does rubber have? It is covalent plus van der Waals forces. So, if we can see, means if we draw the potential energy curve for different material, so as this is having the hydrogen bonding and van der Waals forces, so these two curves represent either your concrete or rubber. Or rubber. So, and as steel and as aluminum having metallic bonding, so it should have the higher energy, means higher negative energy, potential energy. So among which the steel has the highest melting point. So this curve belongs to steel and this is belongs to aluminium. So we know steeper the curve, highest the modulus of elasticity. So among these 4 materials, steel is having the steeper curve. So the correct answer is steel. Now moving towards our second question. That is, which of the following material properties cannot be extracted from potential energy versus atomic distance plot of a material? Coefficient of thermal expansion, modulus of elasticity, toughness, bond stiffness. Can anyone answer this?
Toughness.
Toughness. Yeah, you are right. Uh, so, so if I draw the potential energy versus atomic distance curve, so we can derive the means we can calculate the bond stiffness from the equation df upon dr or dou to u upon dou r square when r equal to r naught. Similarly, from this curve, we can calculate the modulus of elasticity. The equation for modulus of elasticity is 1 upon r naught dou to u upon dou r square, where r tending to r naught. So these two property we can calculate, that is the bond stiffness and modulus of elasticity. What about coefficient of thermal expansion? Can we calculate?
The steeper the curve,
Yeah.
higher the coefficient.
Yeah. As we hit the material, it will expand. So its bond length will increase. So this curve will shift towards the B1, B at K2, A1, B1. So we can see that the equilibrium distance is changing. So from that also we can calculate the coefficient of thermal expansion. So only the option is remaining is toughness. So we cannot calculate. So now moving to the next question. Which statement is correct? Bond energy is directly proportional to stiffness of bond energy curve. Steeper the bond energy curve, higher the modulus of elasticity. Steeper the bond energy curve, lower the thermal coefficient of expansion, and higher the bond energy, higher the coefficient of thermal expansion.
So in fact, A, B, C are correct.
A, B, C are correct. So the only option remaining is
D.
one. Yeah. So we will see. So this is force versus atomic distance. This is potential energy versus atomic distance. So here we know that the bond energy is directly proportional to the stiffness of the bond energy curve. Like higher the bond energy, stronger will be the bond and steeper will be the curve. So this curve will go steeper and steeper if the bond energy is higher. So like if it is like that. So if the bond energy increases, so it will be something like this. So with increase in the bond energy, the stiffness of the curve increases. Similarly, second option is steeper the bond energy curve, higher the modulus of elasticity. We have already seen the modulus of elasticity is nothing but the 1 upon r naught, second derivative of internal energy with respect to the atomic distance, means equilibrium distance. So the steeper will be the curve, the higher we will get, the higher the modulus of elasticity. Similarly, the third option is steeper the bond energy curve, lower the coefficient of thermal expansion. Yeah, we have seen that if the curve is more steeper, then it will take a the bonds are strongly bonded and it will not elongate much. So the coefficient of thermal expansion will be the lowest one. So and the fourth one is contradict to the third, that is higher the bond energy, higher the coefficient of thermal expansion. So in this case, the fourth option is incorrect. So now moving to the question 4. Figure below shows the bond energy plots of two materials A and B. Based on the figure, which of the statements is all correct? So please answer this question, anyone. Mr. Yogesh, Mr. Karthik.
Sir, B is expected to have a stronger bond because it is having a steeper curve.
Yeah.
And then option C, A is expected to have higher coefficient of thermal expansion because since the bond strength is low, it can easily expand. So due to thermal, so option B and option C.
So, yeah, you're correct, Mister. As the B curve is more steeper, so it means the bond are strongly bonded. Means the B is expected to have a stronger bond between atoms than A. So this second option is correct. And then third option, as A is having the lower energy, means higher energy, so it should have the higher coefficient of thermal expansion than B. So only these two options are correct. Now here, the energy potential for a material is given as ER equal to minus 1 upon R to the power 6 plus B upon R to the power 12, where A and B are the constants and their value is given respectively. So find the energy at the equilibrium pressing. So can you solve this one, Mr. Yogesh, Mr. Karthik?
I solved it, but the answer did not match with what they give.
Okay, so what answer did you got?
I got R as 4.168 into 10 power minus 10. And from that E I got as minus 1.38. In fact, correct answer is 1.66.
Yeah.
That's, I don't know, somewhere in the calculation I have gone wrong.
Okay, so we will solve this question. So here we have E is equal to minus A R to the power 6 plus B to the power 12. So we know at the equilibrium distance, the dE upon dr is equal to 0 at R equal to R naught. That is, if you see this curve, that is E versus R, at this point the slope is 0. So we will calculate this one. So if I take a derivative, dE upon dr equal to 6A upon R to the power 7 minus 12B upon R to the power 13. Is it correct?
Yes, sir.
Yeah. So at R equal to R naught, dE by dr equal to 0. So if I will get 6A divided by R to the power 7 is equal to 12
by R to the power of 13.
13. So what I will get? R to the power 6 is equal to
2B by A.
2B by A. So if I put the values of A and B, so what I will get? R naught equal to 3.8 into 10 to the power minus 10 meter. Are you getting the same value, Mr. Yogesh, Mr. Karthik?
No, sir. That is 4.16 into 10 to the power of minus 10. That's all.
Okay. Just do the calculation quickly. So you will get. So this value you should get. That is the 3.8 into 10 to the power minus 10 because I am getting this value.
Okay, sir.
Okay. So now, if I put this R naught value in this equation, I will be getting the energy at equilibrium spacing. So energy at R naught equal to minus A upon 3.8 to the power 6 plus B upon 3.8 into 10 raised to minus 10 to the power 12. So if I put the value of A and B, that is minus 10.37 into 10 to the power minus 78 divided by 3.8 into 10 to the power minus 10 to the whole power 6 plus B is 16.16 into 10 to the power minus 135 divided by 3.8 into 10 to the power minus 10 whole power 12. So I am getting E naught as minus 1.6636 into 10 to the power minus 21. Yeah. So what will be the unit? It will be joule. So this much value I am getting.
Joules.
So,
Okay.
yeah. So
Power of 6.
So in this, the only the second option is matching with my digital values. So this option is correct. So now the question 6. The plane of maximum and minimum values of normal stress differ by this angle in physical plane.
It is 90 degrees.
It is 90 degrees. Why? Because if you see the sigma x is function of 2 theta. So if I draw something like this, so I am getting the highest value at this point, okay, and next highest value is this point. So this whole is 180 degree. So now the distance between these two highest and lowest, that is the plane of maximum and minimum value, it is differ by 90 degree. So the correct option is 90 degree. Now we have question 7. The bar shown in figure has a cross-sectional area of 20 mm square and it is subjected to 100 Newton. Calculate the angle for the plane of maximum shear with respect to the plane where load is acting. So can anybody answer?
So it is coming to 45 degrees.
It's coming to 45 degrees. Okay, so let's see. So if I take this here, so what he's saying, here we are applying 100 Newton. So if I draw the free body diagram, so this is 100 Newton, this is 100 Newton. So let's say, assume this is my sigma, y-axis, and this is my x-axis. Now, the sigma y will be the force upon area. The force is 100 Newton and area is 20 mm square. So it comes out to be 5 megapascal. Okay, and here, as no force is acting in sigma x in x direction, sigma x will be 0, and also no shear stresses are acting. So tau xy will also be 0. So now we know the angle for maximum shear is given by tan 2 theta s equal to minus
of sigma x minus sigma y by 2 tau xy.
2 tau xy. So tan 2 theta s comes out to be 0 minus 5 divided by 2 into 0. So the 2 theta comes out to be 90 degree and theta comes out to be 45 degree. So in this figure, the angle of maximum shear, means the plane of maximum shear, will be at an angle of 45 degree. So here you can see it will make a 45 degree. So at this location we will get the maximum shear. So now moving to the next question, that is, a cubic crystal is loaded under a tension along a 100 direction with a stress of 1000 megapascal. Find the normal and shear stress along the 210 plane, assuming a two-dimensional stress state. Anyone?
So option C, 800 MPa and 400 MPa.
800 MPa and
400 MPa. Option C.
Third option.
option 3 C. Okay. So here what they have given, sigma xx is equal to 1000 MPa. Okay, I am assuming it to be in the x direction, and the direction is given is 100, and the plane it is 210. So now I need to find the angle between this direction and plane. So cos theta is equal to 2 upon under root 1 into under root 5. So it is 2 divided by under root 5. So now if I need to find out the sin theta, it will be under root 1 minus cos square theta. Am I correct? It comes out to be
Yes, sir. 1 by root 5.
1 by root 5. Okay. Now, if I calculate sigma x prime, so it is nothing but sigma xx cos square theta. Sigma xx is 1000 into
2 by root 5 whole square.
2 by root 2 square is 4 and under root 5. So we will remove the under root. So what we will get? Sigma xx prime comes out to be 800 MPa. Now this is the normal stress. Now what about the stress? It is
Sigma x into sin theta into cos theta.
sin theta into cos theta. It is 1000 into 1 by 5 into 2 by root 5. So it comes out to be tau x prime y prime 400 MPa. So the option here that is matching with this one is the third one, that is 800 and 400 MPa. So now here comes the question 9. The normal stress acting on two planes A and B at an angle 30 degree and 60 degree to the horizontal are 30 megapascal and 45 megapascal respectively. If the shear stress is acting on the plane A is 15 megapascal, then evaluate the magnitude of stresses sigma x and sigma y acting externally. So have you solved this question?
No, sir.
Got stuck, sir.
Huh?
Same here. I also got stuck.
Okay, so you got just let me add one slide. So here, okay. So here, what they have given is that we have two planes. Okay. So here, what they are saying, at the plane A, the sigma y prime is given. That is 30 MPa. And here, at this plane, it is given as 45 MPa. So now we know sigma y is equal to sigma x plus sigma y by 2. So I am considering for plane A. For plane A, theta is 30 degree. So 2 theta comes out to be 60 degree. So minus what we have? Sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Is this equation correct for sigma y prime?
Oh, yes, sir.
Oh, sorry, this should be the minus.
Minus,
Yeah. So now
one
I
minus.
put the values here. So sigma y prime is given as 30. That is sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta means cos 60 minus tau xy sin 60. 30 equal to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2. Cos 60 is how much?
1/2.
1 by 2 minus tau xy. Sin 60 is how much?
√3/2.
Root 3 by 2. So if I take the that 20 common and if I simplify this, 60 is equal to sigma x plus sigma y minus sigma x by 2 plus sigma y by 2 minus tau x by √3. Is it correct?
Yes, sir.
Yes.
Yes, sir. So now, if I simplify this one, so what I will get? 120 is equal to sigma x plus 3 sigma y minus 2 under √3 tau xy. Is it correct? Just check. Sigma x minus sigma x by 2, it comes out to be sigma x by 2 plus 3 sigma y by 2 minus tau x by √3. So I am multiplying it with the 2 on the both sides. So I will get 120 is equal to sigma x plus 3 sigma y minus 2 √3 tau xy. Is it correct?
Yes.
Yeah. So this is our equation 1. So now, if we calculate for tau y prime x prime, what is the equation? Minus sigma x minus sigma y by 2, that is sin 2 theta plus tau xy cos tau xy cos 2 theta. So here, what are the values we have given? They have given tau y prime x prime as 15. So if I put minus 15 minus sigma x minus sigma y by 2, sin 2 theta is how much? √3 by 2 plus tau xy 1 by 2. Is it correct?
Yes.
Okay. So it comes out to be, so here if I multiply minus 30 minus sigma x plus sigma y by 2 √3 plus tau xy. So if I multiply on the both sides, so what I will get? Minus 60 is equal to minus √3 sigma x plus √3 sigma y plus 2 tau xy. Is it correct? Guys, please answer. Is it correct?
Yes, sir. Yes, sir.
Yeah. So now, if I write 60 is equal to √3 sigma x minus √3 sigma y minus 2 tau xy. Let's say this equation is 2. Okay, so here we have 3 variable and we have 2 equation. Can we solve this one? No. So if we have the 3 variables, so we need a 3 equation.
Third expression.
Yeah. So now let's say for plane B, theta is equal to 60 degree, 2 theta is equal to 120 degree. So here also sigma y prime is equal to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Okay. So for plane B, sigma y is given as 45u is equal to sigma x plus sigma y by 2 minus sigma x minus
Sir,
sigma.
that plus and minus sign.
Oh, sorry. Here it should be minus. Sorry.
That should be plus, no, sir. First. Oh, that also negative. Okay, correct.
Yeah, that is also. Yeah. Sigma x minus sigma y by 2 cos 120 is minus 1 by 2
1 by 2.
minus tau xy. Sin 120 is also root 3 by 2. Am I correct? So here if you take and if you simplify, you will get equation 180 is equal to 3 sigma x plus sigma y minus 2 root 3 tau xy. So let's say this is our equation 3. So can we solve now this 3 equation? We have the 3 unknown and we have 3 equations. Can we get the values of sigma x, sigma y and tau xy?
Yes, sir.
Yeah. So solve and tell me the answer. Solve me 1, 2 and 3. We will get sigma x, sigma y, tau xy. Sigma x is how much? Please tell me the answer. Sigma x, sigma y and tau xy. What is the value of sigma x? Mr. Karthik, Mr. Yogesh?
So should we go by the matrix approach? Huh?
Yeah, you can solve it directly in the calculator itself. So go to the equation where you have the 3 unknowns. So put that and you will get the. Also, you can go by the matrix approach, but matrix approach will take a time.
Okay.
Yeah. So just simply put it in the calculator, you will get the answer. So you will get sigma x as 49 MPa, sigma y as 19 MPa, and tau xy as minus 4 MPa. So here in this equation, you can see 14 and 19. This option is matching. Okay. So this is the answer. Now continuation of the 9th question is the 10th one. That is, in the above question, calculate the plane of maximum shear. So we know plane of maximum shear. It is given by tan 2 theta s is equal to minus sigma x minus sigma y by 2 tau xy. So it is minus of 49 minus 19 divided by minus 4 into 2. So it comes out to be tan 2 theta s is 30 by 8. So 2 theta comes out to be, please tell me the answer. And 2 theta comes out to be, Mr.
15 degrees, sir.
Huh?
2 theta comes out to 15 degrees, sir.
15 or 75? Let's calculate.
Sorry, sir, 70. No, according to answer, that is 75. Half of it is 37.5. But in my calculation, I did it wrongly.
So it comes out to be 75 degree. So theta comes out to be 37.5 degree. So here we have this second option is correct. So this is all about our first assignment. So do you have any questions regarding the first assignment? Okay. So
This question was a bit tough. Ninth question was a bit tough to solve.
yeah.
Other questions are okay.
Okay. Thank you. So now we will quickly recapitulate what are the things we have seen in the week 2, and then we will try to solve some concept related problems of week 2. Okay. So in week 2 we begin with the Morse circle. So what is Morse circle? It is a technique by which transformation equation for a plane space can be represented in a graphical form or in the form of a circle. So technique by which transformation equation for plane stress can be represented in graphical form or in the form of circle. So we know the transformation equation, that is sigma x prime is given by sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Okay, now and tau x prime y prime is given by minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. So now consider this sigma x plus sigma y by 2 is equal to sigma average. That is the average stress. So now if I rearrange this equation 1, cos 2 theta plus tau xy sin 2 theta. So now do what you can do, you take a square on both sides. So what you will get, sigma x prime minus sigma average square is equal to, the simplification of this equation will comes out to be sigma x minus sigma y by 2 whole square cos square 2 theta cos square 2 theta plus plus tau xy square sine square 2 theta plus 2 sigma x minus sigma y by 2 cos 2 theta into tau xy sine 2 theta. Is my video is visible?
So the screen is visible, but you are not.
Just a second. Just a second. Let me solve the issue. Just a second. That's
Okay.
why the video is not visible. Now it is visible?
Yes, sir. Yes.
Okay. Okay. So now we will get this equation, that is sigma x minus sigma y by 2 whole square cos square 2 theta plus tau xy square sine square 2 theta plus 2 sigma x minus sigma y by 2 cos 2 theta into tau xy sine 2 theta. So similarly, if I take a square of this second equation, shear stress, so what I will get? So I will get sigma x minus sigma y by 2 whole square sine square 2 theta plus tau xy square cos square 2 theta minus sigma x minus sigma y by 2 sine 2 theta into tau xy cos 2 theta. Okay, so now if I add equation 1 and equation 2, adding equation 1 and 2, what I will get? Sigma x minus sigma average square plus tau x prime y prime square. It comes out to be what I will get. So here you can see
Sigma x minus sigma y by 2 the whole square.
this we can cancel out, and we will get sigma x minus sigma y by 2 whole square plus
Tau xy whole square.
whole square. So this equation we will get. So it is free from the term of theta. So now easily we can represent. So if we compare it with the equation of circle, that is x minus a square plus y minus b square equal to r square. So what I will get? So this is our this term, and this is our this term. So here b term is missing, and this is our r square. So radius of circle is nothing but under root sigma x minus sigma y by 2 whole square plus tau xy square. Okay, so now if I represent this equation in the form of circle, so what I will get? So let's say this is my circle, this is A, This A is nothing but sigma average. That is the center of circle. Here on x-axis we represent normal stresses and y-axis we represent shear stresses. Okay, so this was about the Mohr circle. Then we have seen the Mohr circle for different cases. Like suppose if I have an element like this on which this is sigma x, sigma x, sigma y, sigma y. Let's assume this is my x direction, this is my y. Let's assume this is that is tau xy, tau yx, tau xy, tau yx. Let's consider this is my element. So how we'll draw the Mohr circle for this case? So the counterclockwise shear stresses we will take, that is, let's say positive normal stress is tensile and negative normal stress is compressive, and clockwise tau is shear stress is positive and anti-clockwise shear stress is, let's say, negative. So now if I consider a plane, it means face A. So here what I am having, I will be having some sigma x. So this is our sigma, this is our tau. So let's say my sigma x is here. Okay, and how much? And shear stress is acting in anti-clockwise direction, it is negative. So let's say this is my sigma x comma tau xy. So this is for my plane A. Now for B, let's assume this is my sigma y and the shear stress is acting is in clockwise direction. So this is sigma y comma tau xy. So now if I join these 2 points, okay, so here my A point, it is showing A point and this is B point. So now if I draw a circle from the by taking the center as C and radius as CB or CA. So I will draw a circle. Okay, sorry for the drawing. Guys, let's assume this is a circle. Okay. So now what this my C point is representing, it is sigma average. This is representing my sigma x and this is representing my sigma y and this is representing my tau xy and this is minus tau xy. So here you can see the maximum shear stress we are getting at this one, at this location. So this is tau max and the tau max is equal to the radius of circle. You can see easily. Am I correct now? The tau max is nothing but the radius of circle. So the tau max is, radius of circle is given by sigma x minus sigma y by 2 whole square plus tau xy square. Okay. Is it correct? Mr. Karthik, Mr. Yogesh?
Yes, sir. Yes, sir.
Yes, sir. Now if we find the principal stresses, so where the shear stress is 0. So shear stress is 0 at x-axis. So this is our maximum shear and this is, principal stress, maximum principal stress and minimum principal stress. Now here you can see if I minus sigma 1 minus sigma 2, I will get a diameter of a circle. And if I take sigma 1 minus sigma 2 by 2, I will get a radius of circle. Is it correct? Yeah. So now my radius is equal to tau max. So ultimately tau max is equal to sigma 1 minus sigma 2 by 2. Now you got it. How we got this equation? We used it in the week 1 discussion session. So some student asked how this equation has been derived. Now you got it.
Yes, sir.
Okay. So now one more thing is remaining. That is whatever the theta was there in the uh, uh, in real space, it comes out to be twice of that of the in Mohr circle. So theta is in a real space and 2 theta is in Mohr circle. So if the plane is at 45 degree in the real space, so it comes out to be 90 degree in the Mohr circle. So now after this we have seen the concept of strain. So before that, please tell me whether the center of Mohr circle will shift from the x-axis. Can it be here?
Along the x-axis.
Right?
It always center is always lying on the x-axis where it is showing the principal stresses or normal stresses.
Yeah, because in the equation, if you see, that is sigma x minus sigma x prime minus sigma average square plus tau x square. So where the b, that is the y coordinate, is 0. So always the Mohr circle center will always lie on the x-axis. So this you should remember wherever you go. If you try to solve the problem for place condition, and if you have 4 options, and among that 4 options, 3 options is having some y offset, so you can directly pick the option where the center is lying on the x-axis. Okay. So after this, we have seen the term called strain. So what is strain? What is strain?
Measure of deformation.
Measure of deformation. So how much deformation it has taken place? Like we compare it with the original length. So, and it is valid for which condition? It is valid for both elastic as well as plastic condition. Plastic condition. Okay. So and also strain is which quantity? Scalar, vector, tensor? Strain is also tensor quantity. So now just assume you have one cylinder. This is its center with L length, L, and diameter d naught. So now if you apply a force P, okay, on this cylinder, what will happen? It will elongate like this. So what happened here? Its length got increased and the diameter got reduced. So this is nothing but your longitudinal strain. Okay, and this is your which strain? It is lateral strain. Lateral strain. Okay. Now, based on this condition, we have defined the one term called Poisson's ratio. It is the ratio of
lateral strain to longitudinal strain.
minus lateral strain to
Longitudinal strain.
longitudinal. Why we are calling it is as a longitudinal strain, this one? Because the longitudinal increase in length is measured per unit length, and that's why we call it as longitudinal strain. So the longitudinal increasing length is measured per unit length and is called longitudinal strain. So here in the Poisson's ratio, here mu, why I have given the negative sign? Anyone? Why the negative sign is there? Mr. Karthik, Mr. Yogesh? Anyone? Why in the case of Poisson's ratio, the negative sign is there? Anyone? Mr. Karthik, Mr. Yogesh?
Don't know, sir.
Huh?
Don't know, sir.
Okay. So here in this figure, you can see that when I am applying the force on a cylinder, its length is increasing, okay? Means this is a positive term, but at the same time, its diameter is decreasing. It is negative term, okay? So that's why I am giving the minus sign. It will take care of the sign convention. So if I press, its diameter will increase and its length will decrease. So the Poisson's ratio will always come out to be positive. And for the ideal plastic deformation, what is the value of mu?
0.5.
0.5 for ideal plastic deformation. And what is the criteria? That is where volume remains
Same.
and for most of the material, the mu value is
0.3, 0.25 and 0.3 range.
yeah. So we'll approximately say 0.3 for most material. So what does it tell us? That the volume is not conserved when we are talking about the elastic prism. So it tells that volume is not conserved when we are talking about okay. So after that, we have seen the concept of true strain and engineering strain.
Sir, 1 second.
Yeah.
Now you're telling that a negative sign for the Poisson ratio.
Yeah.
Now, irrespective of whether we are applying the compressive load or the tensile load, that negative sign will take care of the overall change in the material.
Yeah, sign convention it will take, because Poisson's ratio is always positive. So
Okay.
if I take the lateral strain, it is decreasing, so it comes out to be negative. So that minus will take care of that negative. It comes out to be positive.
Okay. In the same way, when we apply the compressive load, that
Longitudinal strain will decrease.
Decrease. Yeah. Okay.
Yeah, means it will compress, so length will decrease, so it comes out to be in the minus. So that minus also at that time will take care of them.
Okay, sir. Okay.
Yeah. So
Thank
we
you.
have seen the two strain and engineering. So the true strain, engineering strain, is given by L minus L naught. That is, it is a change in length to the original length. So if I write L naught. So now if I consider it for a very small small volume or small element, so it comes out to be del epsilon del L upon L naught, or L, just simply say the L. Okay, this is for very small volume, means very small element, okay, inside this one. So now if I want to calculate the strain for the whole body, so what should I do? I should integrate it. Am I correct?
Yes, sir.
That is del epsilon is equal to L naught to L del L by L. So this comes out to be epsilon is equal to ln L upon L naught. So now, just a second, guys. So now, from this, if I calculate, that is E plus 1 is equal to L upon L naught. So if I put this value here, so what I will get? I will get epsilon is equal to ln 1 plus engineering strain. So as our engineering stress tends to 0, our epsilon tends to near to that engineering strain. So we have made one comment in this, that is the true strain is additive in nature. So have you understood that concept? Yeah, in true strain we can add it and subtract it and we will get the same results. But whereas in the engineering strain, if we add subtract, we will get a different result. Okay. So that's why the true strain is known as additive in nature. So now after that, we have seen the normal strain on 3D object. That is normal strain on 3D object. So here we have considered the one 3D object and we have applied the stress on XYZ direction and we calculated the normal stress and it comes out to be dou U by dou X, EY by dou V by dou Y, and EZZ dou W by dou Z. Okay, and then we calculated the shear strain for same condition. Shear strain. So simply I will represent shear strain as 1ij half of gamma ij. Okay. So here for shear strain condition, I is not equal to j. Okay. Then also we have seen the strain as a tensor. That is how we can represent strain in the form of a matrix. So Eij is equal to epsilon xx, epsilon yx, epsilon zx, epsilon xy, epsilon yy, epsilon zy. Similarly, epsilon xz, epsilon yz, and epsilon zz. So this is, we can represent strain in a form of a strain, sir. So here this diagonal term represent the normal strain and this represents the shear strain. So only here you can see 3 shear strain and 3 normal strains are sufficient to define the stress as a tensor. So we have 6 independent terms also. Okay. So after that we have seen the strain transformation. The equation for the strain transformation in 2D is same as that of stresses. Like for the stresses we have equation sigma x prime is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. So instead of sigma we will replace all the terms with the epsilon. So sigma x will be replaced by epsilon xx plus epsilon yy by 2 plus epsilon xx minus epsilon yy by 2 cos 2 theta plus epsilon xy sin 2 theta. Also similarly that equation also we can use, that is sigma p cube minus I1 sigma square minus I2 sigma minus I3 equal to 0. So just in simple word, the transformation strain in 2D is same relation as for stresses. Okay. So after that we have seen the Hooke's law in the form of tensor. Hooke's law in tensor form. So what is Hooke's law in tensor form? So the C, what is the C here? C is nothing but the stiffness tensor and it is of the rank 4.
4.
Okay. So now after that we have represented this one in the form of matrix. Sigma 3 3, sigma 2 3, sigma 1 3, sigma 1 2 is it equal to A upon 1 plus mu into 1 minus 2 mu. So this is the representation of Hooke's law in form of tensor. That is 1 minus mu 0 0 0 mu 1 minus mu 0 0 0 mu 1 minus mu 0 0 0 here 0 0 0 1 minus 2 mu by 2 0 0 0 0 0 0 1 minus 2 mu by 2 0 and 0 0 0 0 0 1 minus 2 mu by 2 and this is epsilon 1 1 epsilon 2 2 epsilon 3 3 epsilon 2 3 epsilon 1 3 and epsilon 1 2. So this we have seen, that is the Hooke's law in the form of tensor. Then after that we have seen the stress relation in the isotropic material. So stress strain relation in isotropic material. So what we have seen, that is epsilon x, that is the strain in x direction is given by 1 upon E sigma x minus mu sigma y plus sigma z epsilon y 1 upon e sigma y minus nu sigma x plus sigma z and strain in z direction, that is 1 upon e sigma z minus nu sigma x plus sigma y. Okay, this we have seen the stress strain relation in isotropic material. So after that, we came across the concept of bulk modulus, and it is represented by letter. What is the letter for bulk modulus? K, and it is defined as the ratio of hydrostatic pressure
to the
dilation it has caused. Yeah. So in this equation, if I add all these three equations, so what I will get? That is equation 1, 2, 3. So by combining equation 1, 2 and 3, epsilon x plus epsilon y plus epsilon z, it is nothing but dilation. So it comes out to be 1 minus 2 mu divided by E sigma x plus sigma y plus sigma z. So now if I consider the case of hydrostatic, that is the equal pressure from all directions. So this sigma x sigma y comes to be will be same as sigma m, and it is as it there we have sigma x plus sigma y plus sigma z, it comes out to be 3 sigma m. So what we have epsilon x plus epsilon y plus epsilon z is equal to delta v is equal to 1 minus 2 mu by e into 3 sigma m. Now if I put this value, that is sigma m, that is hydrostatic pressure, divided by 1 minus 2 mu by e into 3 sigma m. So the k comes out to be e upon 3 into 1 minus 2 mu. So this is one relation we got. So if we know the value of modulus of elasticity and Poisson's ratio, so we will easily calculate the bulk modulus of that material. So similarly, we came across the concept of
shear modulus.
shear modulus, and it is denoted by letter G, and it is defined as
ratio of shear stress to shear strain.
Shear strain. Okay. So, and it is given by equation G is equal to E upon 1 plus 2 mu. So, if we know the value of modulus of elasticity and Poisson's ratio, we can easily calculate the shear modulus. There is no need to do the another testing to calculate the shear modulus. Okay. So that is the advantages of using this equation. So now we have almost recapitulated what are the things we have seen. Okay. So now we will try to solve some concept related problems. Okay. So the same question from the assignment. Yeah, Karthik.
So that shear modulus, it E by 2 into 1 plus nu or 1 plus 2 nu?
It is E upon 1 plus 2 mu.
1 plus 2 nu. Okay.
Yeah. So now we will try to solve some problems. So this same question we have solved in the week 1 discussion session. So by using the equation, now we will try to solve this problem using the Morse method. So Previously, what we used sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 equal to 0. This equation we have used, and we have calculated the values of that is the maximum principal stress and minimum principal stress. Now the same problem we can solve using the Mohr circle. So can you solve by yourself and show me the diagram? Mr. Karthik, Mr. Yogesh.
Yes, sir, we will try.
So let's say this is my phase A and this is my B. Let's try to solve. So at A, I have sigma x comma tau xy, and sigma x is 8 comma 2.7. So let's say this is 1, 2, 3, 4, 5, 6, 7, and 8. And here it is, let's say 1, 2, and 3, and 4. Okay. So now my first point is 8 comma 2.7. So let's be 1, minus 1, minus 2, minus 3, and minus 4. So now if I take my first point, that is x is equal to 8. Okay, this is x is equal to 8, and shear stress is counterclockwise, so it is negative 2.7. So it is somewhere around here. That is my A point. Am I correct?
Yes, sir.
Yeah. Now on the y we have P sigma y comma tau y. It is 2 comma 2.7. So if I take 2 into 2.7, so somewhere around here, as this is counterclockwise, the shear stress will be positive. So this is my B point. So let's say this is my A and B. Now if I join, okay, so this is my C point, that is center. Am I correct?
Yes, sir.
Yeah. So now if I take a C as a center and a CB as a radius, if I draw a circle, so sorry. Just a second. So I will get a circle like this. Yeah, am I correct?
Yes, sir.
And this is our maximum shear stress. That is tau max. So how much it is? How much it is? That tau max.
2.7.
Tau max is?
Sorry.
Just don't go with the diagram, just draw to the scale and you will get the answer. You will get something this value. That is 4.03360. Okay. Now what they are saying, calculate the principal stress. So the principal stress is here where shear stress is 0. So this is our sigma 1 and this is our sigma 2. So measure how much it is coming, sigma 1 and sigma 2. Anyone? So it comes out to be 9 point something and this comes out to be 0.9 something. So easily we got the value of maximum principal stress and minimum principal stress on the body, that is 9.036 and 0.9639. Okay, so and the tau max what we got, 4.0360. So similarly, and if you find the orientation, okay, with the plane, let's say this is 2 theta. So this 2 theta comes out to be 41 point something. So theta comes out to be 20 point something. Okay. So similar question, the orientation of the axis, the principal stress with the xy axis in degree. So how much it is? 20.99. And the maximum shear stress is how much we have found? Is 4 point something.
0.
Yeah, this is the easy method that you need not to do the many calculation. Just graphically you can solve. Okay. So now here comes the second question. Is it visible? Yeah. B, as shown in figure, a cube of edge length 2 mm is lying on a frictionless horizontal surface. A force of 20 Newton acts on its right face along the positive x direction. What should be the magnitude of stress acting on this face? Neglect the effect of gravity. Please tell me the answer.
Should be 0, no, sir?
And why?
Frictionless surface, there is no resistance.
Yeah. So, what are the in about stress we have studied? What is stress? It is the internal
Resistance to deformation.
And it is only calculated when the body is in
Rest.
equilibrium.
Equilibrium.
Yeah. So here you can see on this body from only in one direction we are applying the force. Okay. So as the surface is frictionless, so we will not get any friction force as surface is frictionless. So if I am applying the force, it will continuously move to the x direction. Okay.
Yes.
Yeah, so it will not be in equilibrium. So it will not produce any internal resistance. So if the internal resistance is not there, what does it imply? It means no stress is generated. So the only option here is
0.
So now moving to the next question here. The same question, find out the stress.
So going by the formula, stress is load by area.
Yeah.
So but we are applying force on 2 directions.
Yeah, and that too different force.
Different forces.
Yeah, so how will you approach? Did you got it, Mr. Karthik?
So that's what, sir. Whether it's the difference in the this one or whether it will move in the direction of the larger force.
Here I have a body. Okay, so let's assume this is my hand is the cube that is 2 by 2 mm. So definitely it will move in the direction of the higher force, that is in x direction, but on the opposite direction we are applying the 4 Newton. So that 4 Newton and this 10 Newton, so it will, that 4 Newton will resist that material to not to move. Okay, so at 4 Newton it will generate some internal resistance. So among that 10 Newton, only 4 Newton is contributing to the generating of internal stresses. So what will be our force? 4 Newton. So sigma is nothing but force upon area. So 4 upon 2 into 2. It comes out to be
1 MP.
As only that 4 Newton. Okay, if it is 6 Newton from one side and 10 Newton from one side, then for that 6 Newton it will generate some internal stresses, and that remaining 4 Newton will contribute in the moving of the body.
Okay, sir. Okay.
Yeah. So the correct answer will be
1 MP.
1 MP. Yeah. Now try to solve this problem. The energy potential for a material is given as, where A and B are the constant, whose values are 10.37 respectively. Find the force F at R equal to that one and R equal to the B1. So what we have given, the energy A of R is equal to minus A R to the power 6 plus B R to the power 12. So did you got the answer?
Yes, 1 second. First one has 5.222 into 10 to the power minus 25 Newton.
Okay. And for second one?
Second one I have to do.
So for force, if I take a derivative of potential energy with respect to R, I will get a force, that is F is equal to dAr upon will be R to the power
Yes, sir. Yes, sir. Yeah.
13. Am I correct? Yes. Now for A, if I put 6 into A value is given
10.37
as
into 10 to the minus 78.
8.
78.
Oh, sorry, 78 divided by 3.822
822 into 10 to the minus 8.
to the power 7 minus 12 into 16.16 into 10 to the power minus 135 divided by 3.822 into 10 to the power minus 8 to the power 13. So it comes out to be 5.22
5.22 into 10 to the minus 25
minus 25
newtons.
Okay, this is for one case. Now, if I calculate for same 6 into 10 to the 10.37 into 10 to the power minus 78 divided by 3.822 into 10 to the power minus 12 minus 12 into 16.16 into 10 to the power minus 135 divided by 3.822 into 10 to the power minus 8 to the power 13. So EF comes out to be how much?
So this one I'm getting again
I will also solve.
5.22 into 10 to the 15 positive.
It comes out to be.
Sir, there you have left out one power thing in the.
Oh yeah, 7.
10 to the minus 12 to the power.
Yeah, 7. So how much it is coming? So if I get
5.22 into 10 to the 15.
Okay. 5 point. Just let me calculate.
Yes.
So it comes out to be minus 5.22.
Oh, sorry, sir. Minus. Yeah.
10 to the power 15 Newton. Okay. So this is for this is all
Case
about
2.
force. Yeah. Are you saying anything, Mr. Karthik?
Yes, that's what I was telling. That with the increase in R, that is the R is the equilibrium distance.
Yeah. So if our at R naught, our force should be 0.
Yes.
So if you find out the R naught, you can easily find out. Like at R naught, d epsilon by dr is equal to
0.
0. So that R naught also you can find out. So can you calculate and tell me how much it is?
R naught, that is what we have calculated, sir. First problem in our assignment 1.
Yeah. So how much it is? How much it was? 3 point.
1 second, sir. 3.8 into 10 to the minus 10.
3.8
into 10 to the minus 10.
minus 10 meter. So you can see at R naught. So if I draw the force, so this is what we will get. So at R naught, our force will be 0. But if we move towards the left, so the repulsive force is that we will get a minus 5.22. And if I move towards the right from that R naught, I will get a which forces? Attractive forces. So that simply you can answer this. Okay. So now
So that repulsive means a negative we have to consider.
Yeah.
Okay.
Yes. Now next question we have this one. Find the principal stresses and orientation of the axis of principal stresses within the XY axis for the following situation. So can you calculate?
Yes, sir. 1 second.
Very easy. So we will be using the equation sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 equal to
0.
Here I1 is equal to sigma x plus sigma y plus sigma z. I2 is tau xy square plus tau yz square plus tau xz square minus sigma x sigma y minus sigma y sigma z minus sigma z sigma x, and I3 is
0.
sigma x, sigma y, sigma z here plus 2 tau xy, tau yz, tau zx, and then what is this equation? Can you complete? I3
However, I3 is 0. Sir.
0. Yeah. So here we have equation sigma x tau yz square minus sigma y tau xz square minus sigma z tau xy square. So if I consider for case A, that is sigma x is equal to 34 MPa, sigma y is equal to 34 MPa, sigma z is equal to minus 55 MPa. So tau xy, sigma z is 0, tau yz equal to tau xz equal to 0. So here you can see this terms become 0, this becomes 0, here this becomes 0, and this also becomes 0, and here all terms become 0. So now if I write the equation for condition A, I1 comes to be 340 plus 34 is how much?
374.
374. I2 is tau xy is
So minus 55 square minus 340 into 34, that is minus 8535.
minus 8535. This is I2. And
I3 is 0.
if I put sigma p cube minus 374 sigma p square minus plus 8535 sigma p minus 0 equal to 0. The sigma value comes out to be
1 is 0, sir. One of the values is 0.
So let's say this is 0.
Yes, sir.
One value is
24.5 and 349.5.
24.5 and
349.5.
349.5. So among these, the maximum value is 349. So
349.
for sigma 1,
Sigma 1,
sigma
yes.
2, sigma 3, because sigma 1 is greater than sigma 2 is greater than sigma 3. The normal convention that we use. Now for B, I1 comes out to be 410 plus
34.
34. It comes out
minus 371.
sorry, this is minus 371. I2 is how much?
170 square minus of minus 410 into 34.
Comes out to be
42840.
it comes out to be 42840. And I3 is
0.
0. So sigma p cube minus plus 371 sigma p square minus 42840 sigma p minus 0 equal to 0. So sigma we will get the one root will be 0.
Yes.
And another one will be?
Sir, if you apply that quadratic equation formula, but under root we are getting negative. That's
like which one?
Now minus b, that is minus 371.
Sorry, 376. It is 376, I think. That's why. Now check.
Okay. 620.
It comes out to be 91.61 and minus 467.61. Now, what he is asking, principal stresses and orientation of the principal axis. The orientation of the principal axis is given by tan 2 theta is equal to 2 tau xy sigma x minus sigma y. That is orientation of normal stresses. So for A, tan 2 theta is equal to how much? 2 into minus 55 divided by sigma x is how much?
Sigma x is
349.5
minus 24.5.
So 2 theta comes out to be
2 theta is minus 18 degrees.
minus
18.19 degree we can take.
Okay, 19 degrees somewhat.
Yeah.
19 point, okay, let me calculate.
9.5.
Comes out to 19.7. Theta comes out to be 19.7 divided by 2. So minus 9.88.
88.
Yeah. So now for B, tan 2 theta is equal to 2 into 170 divided by minus 410 minus 34. So 2 theta comes out to be
2 into 170.
130 divided by minus 410 minus 34. It comes out to be, and it's tan inverse. It comes out to be minus 37.44. And theta is equal to minus 18.70 degrees.
Minus 18.7.
Yeah. Okay. So this is all about the principal stresses and their orientation. Now here we have next problem. Is it visible?
Yes, sir.
Yeah. So determine the shear stresses tau y prime x prime for the x prime axis inclined at 30 theta equal to 30 degree to the x axis. The stress rate is given by. So what we have given, sigma x is equal to 270, sigma y is equal to minus 210, tau yx equal to 320. So calculate and tell me the answer. So we will use the equation tau y prime x prime is equal to minus sigma x minus sigma y by 2 sin
Sin 2 theta plus sigma tau xy cos 2 theta.
cos theta. Theta is equal to 30 degree. 2 theta is equal to 60 degree. So sin 2 theta comes out to be root 3 by 2. Cos 2 theta comes out to be 1 by 2. So we'll put this value. So minus sigma x is how much? 270 plus minus minus plus.
Yes.
So root 3 by 2 plus tau xy is 320 into 1 by 2. Okay. So this is 480 by 2 means 480 by 2 and means this is 240. 240 by 2 120. So minus 120 into root 3 plus this is 160. So please tell me the tau y prime x prime.
minus 47.84.
Minus 47.84. Also find out the sigma 1 and sigma 2 or sigma x prime and sigma y prime.
Okay.
So we'll use equation sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Here sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta minus tau xy sin 2 theta. So sigma x plus sigma y 270 minus 210 60 by 2 30 plus sigma sigma x minus sigma y 480 by 2 240 240 into 1 by 2 plus tau xy is 320 by 2 160 root 3 and this is 30 minus 240 1 by 2 plus minus 160 root 3. So it comes out to be how much?
Sir, sigma x prime 187.13.
187.13 and sigma y prime
1 second.
240 means 120 150. So 150 160 into root 3
That is minus 127 point.
sigma x prime comes out to be 427, I think.
427, sir.
Yeah. Just check. Sigma x plus sigma y by 2. 270 minus 20 is 60. 60 by 2, 30.
30, yes, sir.
30 plus that is 280. 480 by 2. 240 into cos 2 theta is 1 by 2.
1 by 2.
120. That is 150. It is there. And
no. That cos 2 theta is negative, no, sir. Minus 1 by 2.
How much is theta is? Cos 30. Cos 60. That is positive.
Okay.
Here in sigma x prime. In sigma y prime it is negative.
Okay. Sorry. Yes, sir. 427.12. Correct.
Yeah, and that one sigma 2.
Please.
Sigma 2 comes out to
Minus,
30 minus 120. That is minus 90.
So 30 minus 120 minus 277.13.
Minus
Is minus.
Minus 277.
No, sorry, sir. 367.13.
Minus.
Yeah.
Minus 367.13.
13.
Okay. So now I think you had enough of practice about these questions, like how to calculate normal stresses and like if the axis is transformed at some angle theta. Is it not?
Yes, sir. Yes.
Okay. So now solve this problem, next problem, and tell me the answers. So which equation we will use? We will use sigma n or sigma x prime equal to sigma plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Theta is equal to 30 degree, 2 theta is equal to 60 degree. Cos 2 theta is equal to 1 by 2. Sin 2 theta is equal to 3 by 2. And tangential sigma t, that is nothing but shear stress, sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. So if I draw the free body diagram of that element, it is something like this. So this is 120, this is 80, theta equal to 30 degree. So this one will be my normal sigma n and this will be my sigma tangential. Is it not?
Yes, sir.
Yeah. Tell me the answer. So
Sigma normal is coming up to 5 Newton per meter.
x is 80 minus 120 by 2 plus, as no shear stress is acting, so these terms becomes 0. Here also this terms becomes 0. So that is 80 plus 120 by 2 cos 2 theta is 1 by 2. So 80 minus 120 minus 40 by 2 minus 20 plus 200 by 2, 100 divided by 2. How much it is? 50.
100 by 4, no, sir?
Yeah, sorry. No. Yeah, no. It's 200 by 4. 80 plus 120 by 4. So 80 plus 120, 200. 200 divided by 2, 100. 100 divided by 2, 50. Just see the equation here.
Okay, sir. Sorry.
30 MPa. Now sigma t is equal to minus sigma x is 80 minus plus, it comes out to be 120 by 2 roots 3 by 2. So sigma t comes out to be 80, 200 by 100, 150 minus 50 root 3. So sigma t comes out to be how much it is?
Minus 86.
The formula is right now. That is sigma. Yeah. So it is 86 point. How much? 60.
60, yes.
Yeah. So now you understood like how we'll approach to this problem. Yeah. So this was about our first week content. So I think you had enough practice about week 1 content. Am I right?
Yes, sir.
Yes, sir.
So next week we will try to solve some problems related to your week 2. Okay, week 2 content. And week 2 assignment also we will solve simultaneously.
Okay.
Okay. So do you have any questions in your mind? Doubts?
Sir, in week 2 assignment, we are going to, in the next session, we are going to discuss. Is it correct?
Yes, sir. Yeah, next session we are going to discuss. But tomorrow is one session is also there. So might be in that also they can discuss week 2. Is
Okay,
due date
sir.
over for week 2?
Yes.
Is for assignment 2, that is week 2 assignment, is due date is over.
Oh,
Yes,
sir.
yes, sir. Already over, sir.
Over. So I think most probably tomorrow the next day we'll discuss the questions from the week 2 also.
Okay. Okay, sir.
So how are you feeling about the attending session? Is it good?
Yes, session feels good when our confidence is increasing after checking the whatever the process we are following and comparing the process you are telling also. Most of the things are matching, but whatever if not matching, we are learning the new things again.
Okay. So try to attend as many as session possible. So definitely this will help you in your exam also as well. And if some of you preparing for grade, then also this thing will help, because here we will be sometimes telling the tricks like how to answer the question easily, like what are the shortcuts also as well.
Okay.
Sure, sir.
Yeah. So this was about our today's session. So I hope we'll meet next week.
Sir, last week you took the class on Tuesday, no, sir?
Tuesday, yeah.
Next week?
Next week also I will take on Tuesday. Due to some emergency, I have class today.
Okay, sir.
Okay, so from next week also I will take on Tuesday.
Okay, sir.
Okay. So thank you then.
Thank you, sir.
Okay.
Yeah. Thank you for attending the session.
Thank you, sir. Thank you.
Yeah.